Hello, my name is Travis Brummett, and today I'm going to talk about a model-driven middleware integration approach for performance-sensitive distributed simulations. So first I'm going to outline the problem. I'm then going to talk about what a solution approach should include, and then I'm going to introduce Air Solution Mid-X, and then I will talk about our conclusions. So cyber-physical systems are complex systems of systems, and oftentimes simulations are used to study and reason about these cyber-physical systems. However, if it is a complex system, it may require multiple simulators that may have to interact with each other. Uh, but oftentimes these simulators are developed independently without this interaction in mind. So composing simulation components and deploying federated simulations of these cyber physical systems can be difficult. Therefore, we need some kind of abstraction that permits composition yet does not result in noticeable performance and memory footprint overhead. So the solution approach should have three aspects. The first is uh, it should focus on composability of a simulation uh, while maintaining that high performance. Uh, so this can be approached using the entity component system method of development. And the entity component system, or ECS, uh, favors composition over inheritance, and there is a strict decoupling of the data and logic. It is used oftentimes in game development for high performance. So you have an entity, which is an object that is going to be simulated. You have a component, which is a plain data type describing a single aspect of that entity. And then you have a system, which is going to be a function that implements a single aspect of that simulation object. A system is going to be applied to any entity that has the necessary component. So for example, in this graph, you see our entity has gravity, and the gravity system is going to be automatically applied to that because it has the gravity component. This supports composability because if you want to create a new entity reusing the same components, you can. You just create the entity and add those components to it. Or if you want to add another component here, you can add, for example, color or whatever component you choose. So this does provide us that composability without hindering our performance the way we would like it to. The second aspect to consider is the distribution. So what we want is a transparent deployment of simulation artifacts. Um, and because these simulations are event-based, they really lend themselves to a publisher-subscriber model. So what you can do is you can use the Object Management Group's Data Distribution Service, or DDS, and it is location transparent, uh, which means it can be deployed locally with shared memory or distributed over a network. And it is a topic-based pop sub middleware. So DDS is the open standard connectivity standard for real-time systems. Uh, it defines a data-centric pop sub model for distributed communications. And it is performant because it has a fully decentralized peer-to-peer architecture. So, like I said, it also enables location transparency between processes, applications, uh, because it supports multiple transports. So now that we've talked about ECS and DDS, the next big problem is how do we get these two things to work together? Because they are different levels of abstraction. They each have their own framework. So how do we promote easy and rapid design and deployment using both these tools? Uh, So what we used here was a model-driven engineering approach. So model-driven engineering uh, lets us create a domain-specific modeling language and use generative programming. Um, a domain-specific modeling language is a language designed using a meta model where users can actually build application models off of that meta model. So what it does is it raises the level of abstraction and provides the semantics to bridge the differences between ECS and DDS. Um, so uh, we can also use what's called model interpreters that are associated with the DSMLs or domain-specific modeling languages to interpret the model and build code based on that. So for our solution called MidX, uh, we addressed three requirements. The first was composable and high performance with responsive simulations. So we used the Flex implementation of ECS. Uh, for the second requirement, a transparent federation, uh, we used RTI DDS Connects implementation of the DDS. And then to make a higher level of abstraction to bridge the semantic gap between the two, we used WebGME to develop our domain-specific modeling language and use the model interpreters within WebGME known as plugins. So in the entity component system, uh, as I talked about the composability, we can compose entities such as a circle entity, a square entity, or another square entity, and we can assign components to it. Uh, you can see that in the image at the top of the left, um, where we have the circle entity with the components position, size, and velocity. So these implementations will store these components in one or more arrays. Uh, and then when the systems process over the entities, they iterate over the component arrays, which are allocated in this contiguous memory. And this results in less cache misses and improved CPU cache utilization. And you can see in the lower picture here where we have our entity in an array, and then we have the components rendering and motion, both in an array. When the system iterates over it, it will look at the entities that have both rendering and motion, and it will be executed on that entity. So you can see the first one has both motion and rendering. So whatever system that uses both of those will execute on this entity, but not the next two because they don't have both components. So we used the RTI's Connect DDS to meet requirement 2. And with this, our component arrays are exchanged directly between ECS framework and our DDS middleware. And this prevents redundant copying of memory between the layers. So whatever has already been allocated for ECS doesn't have to be allocated again for DDS. DDS will just use a pointer to that memory location. Uh, so DDS standardizes its interface definition language, a wire protocol format, APIs, quality of service policies, and interface extensibility, making it ideal to meet this requirement of transparent um, distribution. And to increase the level of abstraction, we used model-driven engineering, uh, and we developed our domain-specific modeling language using web-based generic modeling environment, or WebGME. And WebGME is a web-based modeling tool. It allows us to create meta models and then models. It allows model visualization. it allows us to use model interpreters known as plugins. So what plugins do is they are going to be used to generate code that is required by both the Flex and the Connects frameworks. So this code is built based from the specifications of an application model built by our user. And to our left, you can see the application module of our meta model, and you'll see the user is going to build one of these applications, and it's going to have entity types, data types, and functions to represent entities, components, and systems of the ECS. And then it has a connector which has either input or output ports, which is used for our DDS. So whenever the user composes this model, they will add those in to their application as they need. So again, it bridges that gap. So to use MIDX, the first thing that needs to happen is we're going to have an algorithmic model developer who is going to develop the algorithmic functions. Uh, those are going to be shared in a model repository. So then we're going to have an application developer who is going to develop simulation application components and then share the interface specification with another application developer. So whenever this other application developer knows the interface of the previous application, they can build their application accordingly, and then both of those are shared in the application model repository. So then we'll have a simulation system designer who is going to compose and validate application components using our modeling tool. And then the modeling tool is going to generate the deployable artifacts that are needed to run the simulation. So in conclusion, MIDX is highly composable and reusable and maintains performance using the ECS approach. We use DDS for transparent and easy deployment, either locally or in a distributed fashion. And we use a domain-specific modeling language to abstract away the difficulty of composing simulations. So the main things that we provide is modularity, reusability, interoperability, extensibility, and the reduced complexity to our users. There are a few things we can do future work-wise, and that is we can extend our DSML to be more inclusive of various data types. Currently, it only supports 4. We can improve our verification process. So when we build something, an application in our model and add connectors for the DDS, we have a verification interpreter. So right now it only checks based on the topic of the input port to the topic of the output port it's connected to and verifies based on that. And then we can look into dynamic changes to the model deployment. So how can we change where that is deployed after it is started? And finally, we can explore deployment of these simulations on the edge for dynamic resource management and explore that. But otherwise, thank you for your time and let me know if you have any questions.